Okay, my name is 𝗵𝗵𝗺𝗀𝗻. This is a boot camp about gnuplot, the plotting software, and how to make proper scientific graphs for your publications. This is important for all students, bachelor level, master level, PhDs, senior researchers. They all stumble upon this. From the student perspective, they usually work with this Microsoft Excel to make plots, which makes awful plots. Should never use that tool for this kind of work. Excel can be good in other parts, but not in this aspect. So what you can use instead, there is a line of tools of higher and higher learning thresholds and more advanced. So the most advanced stuff and so on is like programming languages like Python or MATLAB, for example. Then you have dedicated plotting, commercial plotting softwares that like 𝗁𝗵𝗁 or Igor is another plotting tool, and so on. But then you have gnuplot, that is a little bit in between here. gnuplot is a free software. You can download it directly from internet and start using it. It's a script-based system, so you write commands or script that you load. And gnuplot is actually pretty advanced. I will say it will solve 99% of all your work you're going to do. Perhaps the strength and the weaknesses with gnuplot is when it comes to like three-dimensional plots and things like that, or animated plots and so on, but that's like special topics. But the most basic straight stuff, you want to create proper graphs, the look and shape which should be correct, it should have correct symbols and so on, all those kind of things gnuplot is perfect for. And the learning threshold on gnuplot is much lower, I would say, than all these other tools. And the whole internet is full of already pre-made scripts of how to use gnuplot, so you can just dig from that community. And I mean, I usually, if I want to plot something that is special, I go on Google, I search for that thing and add gnuplot to it, and then some other person has already made a script for this, and then I just can cut and paste that and so on. So in this boot camp I will go through, and I think I will go through how to make these proper plots. It's about installing gnuplot, making your first plot. It's about plotting from data files. That is the main thing that we researchers are doing. So how to import data files. And so we're going to go through the thing that we call CSV data, comma separated values. Many instruments can export data in that format. If there is some otherwise special format that they use, they usually can export in that. So we're going to work with that kind of data material, and then we're going to talk about how to customize your plots so you can add tailor-made labels and these fonts, adding Greek symbols to your graph, adding error bars, making linear regression to your data sets, adding those regression numbers that you get from that fitting into the data plot itself. And also I'm going to talk about more advanced things like when you want to do a post-processing of your data, like you want to integrate your data, for example, how to do that. And then we're going to plug in another tool called the 𝗁𝗀 programming language for that, which is also very handy. So that is what this boot camp is all about, how you as a student can make a proper graph for your publication. All right, so let's look on a proper graph here now. Here I have, can I make it smaller? now it fits. So here we see a proper graph, one type of graph one can make. So what is this? This is from an experiment in where we're measuring the resistance of a material that has been coated on a substrate, so the electrical resistance. So what we're doing is we take two probes that we're measuring the electrical resistance between these two probes on this material, and then we change the distance between the probes. So we get the resistance versus the length or distance between the probes. So here we have the dimension length, it has unit centimeters, and here we have the resistance, and we have the unit of ohm here, or kiloohm. And in a proper graph you have this variable that depends on something you have on the y-axis here, and the one that it depends on we have on the x-axis. So the resistance depends on the length in this case. And the data points, that is the squares and circles. So we can see that there are 4 data sets in this same graph here. So there are 4 different experimental runs that have been done here, measuring the resistance. So the dots represent the data, the measurement, actual measurement, while the line is the model. And here students always confuse these things. When they come from the Excel world, they tend to make the thing called line point plots. So they make a line between these points here in the graph, and that makes this zigzag pattern. So because the measurement data always have some kind of measurement errors within it, so that make them a little bit offset from the model in one way or another. And that if you make a line between the dots, then what you're actually saying is that your model is trying to replicate that you don't any longer think that the deviation from a straight line is an error. You're thinking that the deviation is actually a true, what should I say, proper value that you have measured, and your model is taking that into account. And that if you have like as many data points as we have here, like hundreds of them, it will be a very, 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 very complex model for you to describe that kind of behavior. So most of the time that is not the case. The model should be as simple as possible. And when it comes to this kind of measurement here, we know that the resistance should be linear dependent on the length, as long as the material is of the same thickness and so on. So here the line represents our model of how we interpret the situation. So the slope of the line, that is the resistivity of the material. So this is a smart way of measuring resistivity of a material. And the intercept on the y-axis is the contact resistance between the probe and the material itself. So by making this type of measurement, we can distinguish between the effect that is caused by resistivity and the effects caused by the contact resistance. And we are interested in the resistivity in this case. So here we can see for the solid line here, we see that the resistivity is 3.81 milliohm-meter. And that the error of that number is 0.17 milliohm-meter. So in a proper graph, we want to present our model. That is sort of the highlight of our study, to see if the model fits with the experimental data. That is the scientific method. So, and the result of that model, these numbers, comes from a linear regression that were made to fit that line to the data. So we want to present those numbers directly in the graph here. And besides having those kind of things presented in your graph, you also should have a proper title also as well, as we have here. But then you can talk about the colors. The colors of the graph is like, it's good to follow this rule. Stay away from colors if you can. Because if this is going to be printed printing color demands color printing technology. So if you print a color graph in black and white print, some colors might not be shown. It can be too light gray or something, and they tend to look bad basically, and it can be hard for the reader to see what's going on in your graph. So black and white is the way actually to prefer this, and to have it as most black and white compatible as possible, you can as in this case have different symbols instead of different colors, solid, circle, and squares and so on. And also on the lines you can use solid lines, broken lines, and so on. There is cases where colors actually can be useful. I mean, if you don't have a traditional graph like this, but it can be like a plot of intensities in a two-dimensional domain or something, colors can be useful for that. But it can also be, if I take another example that I can put up here, is this case. This is, oops, did I remove it? Yeah. Aha, it's okay. So here it is, yeah. So in this is a cyclic voltammetry graph. So here we are measuring the current as a function of the potential. And in cyclic voltammetry, it is quite common that besides this first variable, you also want to study the current as a function of a second variable, and that is the speed you are looping this potential with. And that's called the cycling speed here. So we see here that we have different speeds. And here it's very traditional in this field to actually use colors, and we can see that that is quite smart here, because there's a natural interpretation that we can directly see the variation in this second parameter, because it has this kind of rainbow color palette linked to it. So we go from this black blue stuff up all the way up here to red, so we can immediately see how that parameter affects our data. A black and white version here would not be such a proper way of doing it, because then we need to use different types of broken black lines and solid lines, and that is not easily interpreted when we look on it. So to understand which sort of dashed line type represent different speeds. So these are just two examples. So tip number one, stay with black and white, right? How to download gnuplot then? Well, you go to the web page gnuplot.info, then you come here, you click on download, and here, and then you can choose the latest recent version here, and this is for Windows. If you have Mac and so on, you can find that as well, and Linux, you probably know already how to get that. You download that and install it, and I can also mention that there is a user manual here that one can look on, and also this demo gallery, because gnuplot is a script-based plotting tool. You have some small code snippets to make your graphs, and if you go to this demo page, you can see how to make all different types of graphs. So if you have, for example, how do I make error bars in my graph, you can click here. Then you get several examples of different kind of error bars, and then you see the code snippet here on the side. So then you can just cut and paste and use that in your graph. So that's usually what I do. So download that, and then you install it. So we can remove this here and install it, and then you will get something that looks like this. So as I say, it's a script based, no icons and things like that on this gnuplot thing. So you can write the command directly here. And let's say we make our first graph. The plotting command is plot. And let's say we just want to plot a mathematical function. So let's say we want to plot x to the power of 2. So double star means power of 2 and 2. Then I get this. This is our first graph. It plots in this window that pops up, and in what as I say, I would recommend against plotting directly into this kind of window. we can, I mean, as a researcher, sooner or later you want this to be a file that will be going into some publication, right? So why not print it directly to the file instead of clicking save here on all your graphs? And especially if you changing this, then that it changed the file and so on. So if you want to sort of come back to your data and so on and replot it and so on, working with this window is not a very good option. The only good thing with the window is that you have these coordinates down here, so you can go in and measure in your graph manually here. So for that it can be useful, but otherwise I recommend against this. And the output of the plotting, that is controlled in gnuplot by something called terminal. And here you see it says terminal type is vxt. So this window is called vxt. If we want to plot a file, then we must switch terminal. And all file formats are different terminals. So a PNG image file is one terminal. You can have a PDF file, which is a vector-based graph, which is much more preferred than PNG. That's another terminal. You can have a PostScript terminal, and PostScript is, what shall I say, more customizable code that is made, that is recreating your graph. And the capabilities of your plotting depends on the terminal. So if you're using this vxt terminal, that is extremely limited in its capabilities. If you're plotting to image files like PNG, that is also quite limited. If you're plotting to PDFs, then you can use something called the enhanced mode, and that allows you to add like Greek symbols and things into your plot. And it's also, you get it to be vector based. So that is a step up, right? And that's the level we want to achieve today in this bootcamp. In the PostScript version, that is the highest level of advancement you can have in customization in your graph. Then you can add like latex math formulas directly into your graph. You can have labels that you import from your other text document into your graph and so on. But that is outside. I mean, if you need that, then you probably have become advanced on gnuplot already, so you can figure those things out yourself. This bootcamp is taking you from Excel that creates awful graphs into gnuplot that allows you to make proper graphs. So normally we don't write the commands directly in here to generate. We could technically do that, but then you need to re-enter all the commands every single time that you're coming back and want to remake your graph and things like that. So it's much better to save all the commands into a file, and that is what we call the script file. So we can just take a new file here. I save that as I do like this. I put it up here now. So I just made a file. This is just a text file. I let the ending be PLT for plot, but you can have TXT text or whatever you like there. It's just a text file. This is a Notepad++ text editor, but you can use the Windows Notepad as well. That will be perfectly fine. So here we're going to write our commands now. So the first command we're going to run is the command called reset. And reset, as it says, it resets everything. So this is useful if you have several files that you're plotting when you're working. Then if you don't reset, then configurations you have done in the previous plot might move over into your new plot, and that might corrupt your presentation of the plot. So it's always good to start from square one. So we write reset. The other thing is to choose the terminals. Okay, we want the terminal to be a PNG file this time, right? So that's the first thing, right? And then we also need to tell what the file, the image file should be called. So then we choose set output, and then we just choose some name here. We let's call it plot1 or png, like that. And then we can make our plot command again here, like that. Then it will go to the file instead, and then I write unset output here. And the reason for that is that the gnuplot will keeping the file locked during this operation until you get the unset output command. And so when unset is done, it releases the file to the operating system. So then it doesn't interfere if you're trying to copy the file, things like that later on. If it's locked, it will hinder you from that. So we do that. I save this, then I can go here and load our script. Plot1. Open. It has loaded, didn't see any errors, right? Then I can just open the file editor like so, right? So here we have the file editor, and I can open that plot. So now I have the image PNG file here, right? All right, so we can configure the terminal also. So let's what are the sort of most frequent commands. The first thing is the size of it. So if I look here on the file, it says it's 640 by 480 pixels. If I don't want that, I mean, if it's going to print, you probably want to have a higher resolution if you're working with bitmap images. So then we can add here and say the size should be like 2000 by 2000 pixels. So let's do that. And then go here and rerun the command. Go and look on the plot. Now the plot looks like this. But notice now that the scale is here like super small, right? The font is very small, so we need to change that as well. So we can go here and say that the font should be, what type of font do we want? Perhaps we want Times Romans this time, and the size should be larger. So let's try 30. Now we have some numbers there. It's almost too small still, but I think it will be okay. Yeah, we can fix that also. But then the next part to look for here now is the axis here, right, and so on. That we would like to change as well, and we need labels and so on. But before we're doing all that, there's no point in plotting a mathematical function in this case. I mean, the purpose is, our goal here is we have the data set and we want to make a plot of that. So we're going to plot a data file now instead. So this will be our second plot, that is. So then we can take this file here, we just copy that and call it file number, plot file number 2. So this is usually what I do, and then I can, now I change the file here, and then I can modify this. So here we're going to plot a file and a data file instead. So what data file do I have now? So here I have a data file. This is from electrochemistry. So this is potential stat data. It's cyclic voltammeter we're talking about. And here the file comes, it is actually an XML file. You can see that you have these brackets, and then we have these brackets with the ending slash there. So these are XML documents here. But besides that, if I go down, you can see here comes the data now. So if I make this larger, you see the data are comma separated values, or what as we call CSV files. We can also see that it's not a comma that separates the data, it's a semicolon. And if we're going to make a cyclic voltammeter, that means we are interested in the voltage and the current. So we want to see the current as function of the potential. And if you look here in the definition, it says it's column 3 and column 4. So first, this is the voltage and this is the current, right? Those are the data that we want to plot. All right, so we go here. I take the data file. I add this file name here instead of the mathematical function, and I want to plot column 3 against 4. So the first number is the x dimension here, and the second number is the y dimension, and they were in that order. So the current is, we want that on our y-axis, right? So they should do like that. But before we can run this, we need also to tell gnuplot that the data file separator is semicolon, right? And also, depending on what kind of country you are in, it can be sometimes useful to also tell what kind of decimal sign you are using. And in this case, it is a period. Sometimes it's a comma. So let's try this now. Yeah. Plot 2. And here we can see the data, right? So here, this is cyclic voltammetry of a supercapacitor. So we get that this kind of squared shape function when it goes. But now we can see, okay, what we can do something about scales here. You see, there's several things that is wrong about it. The first thing is that this region is empty space. So we want the scale to go from 0, not from -2, from 0 to 1. And also we can look on the y-axis here. It can be good if that also goes from like -002 to +002. So let's fix that first, and we can also change the size of the font there a little bit. Make it a little bit bigger. So let's make the font a little bit bigger. Let's try 40, and then we want the range there. So if I make these brackets here, so the first bracket is the x direction. I want that to be from 0 to 1. And this other bracket, I want that to be from 0, 0, 2, right, was the upper one, and -0, 0, 2. So then I can just write that 0, 0, was it 0, 2 or 0, 0, 0, 2? Let's see if it was 2 milliampere. I think it was 2 milliampere. All right, so now you see we have the correct ranges there that we wanted. But then we can do more formatting on this. And for example, if we look on this axis again, you see this. Instead of having 0, 0, 0, 1, 0, 0, 2, and so on, it would be much better to change the unit here. But what is the unit? We need to add the label first. So let's add some labels. So the X label, what's that? That is the potential measured in volt. The Y label, that is the current that is measured in ampere on our data, right? So if I just going to check that, and it looks like this now. So now we have some labels here. But as I said, having the unit ampere here makes very small numbers. So why not change the milliampere instead? That means we want to process the data. We want to make the data 1,000 times larger. So then we can say that we go here, and we're in this using part. We add brackets around the 4. Then it will be a mathematical expression that we can have there. But then we need to refer to column 4. If we have just the 4 within the brackets, it becomes the number 4. So if I doesn't have the brackets as on the tree here, that is like a short version of actually writing brackets $sign for. This means the fourth column. And then I want that to be 1,000 times larger, right? But then I need to change the scale here on the y-axis also, because now it will go from -2 to 2, right? Because it will be milliampere, and then add the symbol here, milli, like that. Then I can plot, all right? Looks much better, right? Now we can also see that, you see here, say 1.5, and then it will be -1, minus 0.50. It looks much more professional if it would say -1.0 and -2.0, and also here 0.0 up to 1.0. So we can add the formatting to the x-axis, and then you use the format commands from, if you have doing some programming, you know what this is. But there is some codes that you write, and the most basic code is to format a float number, and that will make a percentage sign like this, and then you tell how many characters long it might be. And in our graph here, it is like 2 numbers and a dot, so that is 3 characters, and the minus sign, so that is like 4. Can be up to 4. So let's say I write this 4, and then I write a dot and tell how many decimals do I want. I always want 1, and this should be a float number. And the same thing we can do on the on the y-axis as well, like that. You can plot that. So, oops, what happened there? Oops, the percent sign ended up in the wrong place. Like that. So now we see you have a proper decimals there. We can add a grid. Let's add a grid to our graph. So now we have a grid also. But what about the spacings between the ticks here? I want to have a different spacing there. So let's say I want the x spacing here to be a little bit tighter. Instead of 0.2 on every 0.1 would be nice. So we can add that, set x ticks to be 0.1, and I can also say y ticks, but y ticks was quite good. I think it was 0.5 on the y, so yeah, you can leave that on 0.5 then. Now it looks like that. So now the graph starts to look pretty good actually. There is this thing on the top here. That is the legend that describes this data set. So it's a little bit crowded up here. So I want to move the legend down here. And then I also want to make a proper title of that. So then the legend is called key. So set key. And then I choose some letters here. So B for bottom and R for the right side of the bottom part. And then the title I can add here. The title should be my data set, right? Make a new plot there. Go back and look. So now it says my data set. And if we look here now, it says, if you see there's a little dot there. So our data is plotted as points, or not points but dots. As I said, the graphs should be black and white in the beginning. If we can, that is the preferred way, and use some symbols and so on. So let's change the style of the graph now. So to add some style, we can I get this all to fit on the screen here? Can compress these things. So then we write set style 1, and so we can have many line styles, and then we can choose line color, and one can write a number here. There are predefined colors for numbers, so I can choose color 1, but I can also write the RGB color of black. I can choose if I like that, or I can write like this hexadecimal number of a certain color also. And then I can define more in my line style. Perhaps I want what kind of line type do I want? Let's say I want to change it into a dashed version or something like that. So we can have one dash type 1 is just a solid line, so that we can start with. We can change the line width so it's a little bit thicker, right? Too. And we can choose a point type. Let's take point type 4 for this, and the point size can be 1. So a larger number means a larger point size. So let's make 2 at the same time here. So we can make a second style here also, and the second one can have a different dash type. So let's say that this has this will be a broken line. We use a dash type 2 here. All right. And then I want my data to use the line style 1. So let's try that and see how it looks like. What happened here now? Oh, I forgot. It's just style line. Set style line. All right. So now you see it turn black, right? And we can also see that the data points are squares now, not just the dots. So here we see the data are very dense. There are very many data points, like 1000 data points here in each loop here of the graph. So it looks like lines, but they're very closely spaced data points. So that is also an interesting topic. How about if I want to reduce my data set now? So let's practice on this data set. If the data set is very large, like let's say it's 1 million data points, it will take forever for the computer to plot that on screen. It's very not practical to work with. So then there is something called the every command here that we can add. So if I just write every and chooses, let's say 50, it will only plot every 50th data point in the data set. So it takes out, it reduces the data set by 50 times, right? So let's do that. Now we can see here that the data set is much less reduced, and right? And it's when this cyclic voltammeter is running, it makes several loops, so that's why the data comes back again here also. So it's not just one graph where it goes round. All right, so the only thing remaining in our graph here, that is that we want to have a title of the graph, right? Set title cyclic voltammetry of supercapacitor, right? And if we're doing a proper cyclic voltammetry graph, we don't usually want to have remove data like the thing we did, so we can choose to plot every single data. And then we don't, because data is so closely spaced, we could actually do this polygon train, making a line between each point. So we make a lines instead, right? So then we can add the command with lines. So then it will not use the, it will just make a line between all the data points. So now it looks like that. So here is my data set, and we see the line there. It makes a line between all the data points there. In cyclic voltammetry, it's quite common that you plot it like that. You don't do like a modeling in cyclic voltammetry. It's quite rare. All right, I can open the data file. Here is the data file. So here we can see we have how this was how the graph looked like, right? So we had 4 different data sets, resistance versus length, right? So here the first column is the length measurement in centimeters, and if I scroll down here we can see it starts. So here we have all the 4 data columns here now. So let's choose just take one of them. We can take the first column here, and the first column will be this line, right? So let's remake basically this graph more or less. All right, so let's say this plot2 into a new file called plot3, and we copy that. Like so. Here we have plot3. We want to have the new data set. That was called, a very long file name on that. Yeah, it shoots over. It shoots over to a new line here. Okay, so that's its data set, and then we have the x dimension was on the first column, and the resistance there was the second column we wanted to plot, right? And if we go back there and looking on the data, we see that it is measured in kilo-ohm, right? So it is a kilo-ohm range already, so we don't need to do any manipulation of the data. We can just plot it to column number 2 directly here. So we can remove the brackets and everything as well. So okay, and now we have here on the x-axis we have the distance, right? And that was in centimeter. And here we have the resistance, and that was now in kilo-ohm, I mean. So this should be kilo-ohm here. So it's kilo first, but then we need the ohm sign, and that is like this Greek symbol, right? So for that we need to change now. The PNG cannot handle that, so we do a PDF file now instead. Change terminal, and we also change the file name of our file also. But then the size is not measured in pixels anymore, because this is a vector-based format. So here we have proper physical distances like centimeters. So let's make it 20 by 20 centimeter, our graph. We can try that. We can make it perhaps a little bit longer in one. We'll see. We'll start with that. And then the font here is also different now. So now we need to change the sizes. So try something much lower here now, like 15. And then we can add the symbol here. So then there's a certain special code snippet that you add here. And you can find if you Google on internet for a file called the PS dash guide PDF, then you come here. So here you can see if you want to make a superscript, you write this curly brackets and this up arrow, this down score and brackets and subscripts and so on. And then one can go down here and look for symbols, and then we can see, okay, omega symbol, where there it is, right? So it has the it has a symbol W here. So then you write like this. So you make curly brackets slash symbol W. That means omega, and then I have K here because it was kilo-ohm, right? Let's try that. This is plot number 3. See, we need to change the range here also. So let's choose outer range here instead. If I make a star here, then it means outer range. Like that. It looks like this now. and you see now the X ticks and everything, we need to fix that, so let's fix that. The Y ticks was quite good, but X ticks, it was in centimeters down there, so perhaps 5 centimeters per tick would be nice. So let's start with that first. Then the graph looks like this. We need to change the title, of course. It says resistance, and we have the Greek symbol there now, right? And it says distance here. And then you see we have this decimal sign here that is not valid anymore because it's even numbers down here. So let's fix all that. We go change the format in the X direction. It is only 3 numbers wide if it's 100 centimeters and 0 digits after the decimal mark. The title is now resistance versus distance, like so. Let's redo this. So now it looks like that, right? Yeah, so distance looks nice. Here is the data set label. So but now you see we are making lines, still lines between our data points. So in this case, this is not a proper way of making the graph, right? Because we don't believe that the resistivity is actually following this line. We think that the data points has some errors to it, and the resistivity should be a linear line, right? So let's change back our data now to plot only points. So I want to make points now, not the 3 different things. You can make dots, that's just 1 pixel dot. A point is this specific symbol. A line, that is a line without points, and then you can also have lines points, that means lines and points, so lines between the points. But we only want points now. So now it looks like that, right? But we see that the point size is quite large for the data is very close here. So make the points a little bit smaller also. So let's try 0.8 or something on our point size. Yeah, that is better, right? Now you can see the points are individually there, right? So let's add a linear trend line there. So then we need to make regression on this. That is very easy in gnuplot. So we need to define a function. Let's call that the f of x, and it has a constant a times x. We want a linear function, so we run a times x plus b. And then we want to fit that function to our data. And then it actually is the same syntax as we're writing down here. We can all the way over here. So if I just copy and paste all that. So I can choose if I want to fit the data within a certain range of my data. In our case, that is not needed, so we don't need that. I want to still fit versus the same columns, of course, so that must be true. And I can also change here if I want to skip data and so on, but we don't want that either. So we just need this. This is the only thing we need now. But then I also need to change that the fitting variables should be a and b. I mean, I can choose to only fit to a, for example, and give an explicit number for b. That is of course valid. So if I run this now, it do that fitting here, and we see the parameters. So a should have this value and b should have this value. And here we have the standard deviation errors for those. But then I want to add that to my graph also. So we need to add a new function here. So if I want to make several plots, I just make a comma, and then I want to plot my function. But if I have lots of functions that on data files are going to plot, this will be a very long line. So then I can make a backslash here, and then I can start on a new line. So that is a way to cut the line. And then I choose I want to plot this with line style 1 again, because now you see we're using only points here, and then we were using only lines here on our function. That is the default lines. So let's plot this now. Yeah, we can also add a title to it. So here we can call it, this is our model, right? And now it looks like that, right? So here we can see the line added, representing our model. It should be a linear model that we are assuming here, right? Which is correct, right? So how about the values now here? I want to know the resistivity here, right? So let's adjust our function first now, because the resistivity of the material, it depends on, I mean, we are measuring the length, right? But we need to know the cross-sectional area. So we need to know the width of this stripe we're measuring and the thickness of that material, right? So let's add those parameters. So the thickness of this material, let's look on that. What was it from our old graph there? 25.4 micrometer. But we have the width of the strip, and the width of the strip is 25.1 millimeter, right? Alright, so that is the thickness and the width. So then we can modify our function here. We can make a new function. So the resistance of that we are measuring is actually the resistivity rho times, and what it is, like the larger the area is, the lower the resistance becomes, right? So it is times x, right? And then it is divided by the area, which is the thickness times the width, right? And then we have some initial contact resistance R0, right? And then this means also, if we want to have all the units in proper way, and remember that X data was in centimeters. So we should actually translate that into meters here also, right? So we change that to meter, and then we have everything in meters. So then we will get the resistivity now in ohm meter. But the resistivity of the data set, when we look on data set, we see it's milliohm here. So that means the final value will be very small here. It will be in milliohm. So let's try that. And then we fit this data, this function to the data now. So change this to R of X and fit it versus rho and R0. Then we see here that rho is 2.4 microohm meter and R0 is 0.18. But it was in kiloohm, yeah. The Y values is in kiloohm, so we need to compensate for that, right? Like that, right? So now we're taking it out that the data was in kiloohm also. So now it says rho is 0.002 ohm meter, right? That is 2.4 milliohm, right? You can look on the old data here, it says 2.4 milliohm data. And the contact resistance is 188 ohms, right? So if we want to plot that function now, so we can plot R here now instead. Then it looks like that, right? So there we can see the data on the screen now, 55%. Okay, so I mean it's still the same line, but we want to have those numbers now written inside the graph, right? And the best way to edit it is directly here to the title of that function, right? So then we replace this. We don't write a string here. We want write sprintf here, like this, and then we write the string. So our model, what is our model? That is that the resistance as a function x is equal, and then we want this this rho symbol, right? So we can go and look in the data file there. Where was that now? Here is the PS guide. The rho symbol, where is that? There, it has a R. We're going to use R here. So R, that is the rho, right? Times x plus R0, right? That is our model. And then we can explain that this symbol is equal, and then we write our format, and we write that as a decimal number in milliohm, right? So it will be milli, and then the symbol omega, right? And it's ohm meter, right? Milliohm meter. So that's the first part there, and then we can add R0 is equal to %. We can do that without digits, right? Because it's 188 ohms, right? So it comes like that, and we should have the ohm symbol. And then after the comma here, we add the parameters rho and R0, right? But rho was very small, that should be in milliohms, so add 1000 there on that. Let's now look how it looks like. So now it says here, this is the model, right? It is rho times x plus R0, and rho is 2.4 milliohm meter, and R0 is 188 ohm. And no, this 0 should be a subscript, right? And also I forgot to add the area here into the formula, of course. So we should change here. So it should be divided by the area, right? And R0 should be subscripted like that, right? So now we see R0 is subscripted, then we have ohm symbols, and it's rho divided by times x, which is the length, right? So if you have come this far, now this graph is actually perfect now. We have the proper symbols, we have, in this case, example of using Greek symbols in the labels. We have a regression line to fit into our data there. We have written out the model that we're using here, and we have automatically inserted those regressional numbers there into our data there. All right, so there's not so much more we can do about this data set. There's something we can comment on, and that is the range that we're fitting on. As I told you, we can change the region that the data is being fitted on. So now it looks like this, right? If you look on the original graph, we had other data sets here. So we have, for example, this one here. That is a nice data set. That is the first width section. So let's replot with that data set. So we can use the same plot file and everything for that. So we change that's the column 3 in the data set, I think. All right, so here we have column 3, right, the widthwise section. So it's a little less data now. You see it's only 60 data points. But look here now. Here we have one error. That value is very low there. And then it deviates from our linear trend here. So here there is some corruption in the data. So let's say we don't want that to be part of our fitting. We want to start our fitting from the 10 centimeter here and forward. So let's do that. So we tell that the fitting should not be from 0. It should be start from 10 and continue to the end of the data. Right? And then if we just do that, then everything will be fine, right? It will fit the data to that, it will disregard that, and we get some other numbers now here. You see now we have a higher value there, it aims there at 1 kiloohm, and we get 3.8 milliohm here now. But it would now the fitting starts from the 10th here, so I don't want the line here to be shown here, because then I extrapolating this data down into this region, so it will be not correct to have a line there if it's fitted to the other. So I need to shorten that trend line. And I can do that if I go down here. It says Rx here. So here we write the range of the data, and we can do the same thing here. I want the range of my line to start at 10 and continue. And then we see here, now the lines has been shortened there, so it starts from 10 there. Can I get it on screen? So there we have the full graph, right, with the trend line there. All right, this other data set that looks like this. So still a comma separated values here, a CSV file. But now you see we have errors, error column. So here is the B column is the coating thickness, and then BE is the error measured for that parameter. So we have a specific error value for each data column here. So there's an error column that follows all the data columns. So now we're going to make a plot of that. So then we can add error bars or figures that are, what shall I say, point specific. For each data point is a unique error bar. And also we're going to, if we look downwards here, you can see the data file goes down here, and then there's a gap here. So there's the data is divided into like 1, 2, 3, 4, 5 data blocks, and we only want to plot one of these data blocks as well, so we can practice on that also. So we can copy the previous plot file. I think that can be a good starting point. So let's do that. Call this plot number 4 then. Here it is, right? It's just a copy of plot number 3 and close number 3. All right, so what we're going to do here is we want to plot, if you look here, so we want to plot the resistivity, the D column resistivity versus the density of the material. But we can, what you see here, that the density of material, it doesn't have a separate column. We only have the coating grammage here. That is how much mass of material we put on per square unit area, per square meter. But then we also have the thickness. So if we take the coating grammage and divide by the thickness, then of course we get the density, right? So our here we're going, the title is resistivity versus density, we can call a graph that. And the X label is the density, right? And if we look on the data there, it says that it's grams per square meter. And then thickness is micrometer. And it turns out that if you just divide those straight on, you will get grams per cubic centimeter as the unit. And here X label is resistivity. And we want to use the rho symbol for that, right? And the unit of the resistivity will be 𝗵𝗵𝗋𝗋, right? And the data file, add the data file there. That's the text. We can remove this other part now. Start just here, can remove this fitting part thickness. So start from scratch here. All right, so let's try this. But okay, what is the columns now? So if you look on the data here, we see that it's column 4, that is the grammage, right? And column 2 is the thickness. And column 6 is the resistivity. So we would like to calculate column 4 by division of column 2 versus the data in column 6. That should do it. Let's see, plot 4. We can choose auto on the tick scales in the beginning here, and we have out on the range also. So let's try this just straight on. Load plot 4, and then we look on the graph. So here is the graph. As we see, the data are located in a very broad range. You see, we have some very large values here, and then most of the data is here. So this is not a linear data. So here we would like to have a logarithmic scales on the axis here. So that's the first part that is unique with this data set that I want to show. So okay, so set log x means we make x scale logarithmic, and then the division of this log scale, you can have a power of 10 or or power of 2. So I like power of 2. So let's do that in both x and y. Then we can replot that. Let's see how it looks like. So here we have the data now. And then, as I said, it was 3 data segments. So let's practice on that now and pick out one of the data segments there. So remember, before we have plotted like data has been in different columns, but now they comes in different blocks. So we want to pick out the right block here. So a nice way here, you can always write help here, and then you can look on the every command. So when we use the every to make, as we did before, plot every second or every 50th point of the data file, this command is more advanced than that. So what you can see here is that we can, for example, write these semicolon things. And here it says that it plots just the 4th block. So 0 is the first. So block 4 to end of block 4, so to say. So this is exactly what we want. So if I add this instead of every one here, there, like that. If I write like that, it plots the first block of the data part. That is this top part here, and then this will be block 1, this will be block 2, because this was block 0, right? So let's do that. And then I add this comma because I want to plot everything again. And I can also add a backslash there so I can put it on a new line. So the backslash means new line. And then we copy this like that and plot the second data block like that. And then we can take another line style for that. So this is the data set number 2, data set number 1, right? All right. And then we can go up here and look on the data set here. It says we have different dash types, but the same point type. So let's change the point type to, instead of a squared box, we can make a cross X mark. That's point type 2 there. And we can also, just to clarify it, we can make one of them red also, so it becomes easier to see. Let's replot. So now we see we have the 2 data sets here. The first data set and the second data set there. And the first data set has less accuracy. We see there's some more deviation in the data points there. All right, so let's add error bars to this now. So how do we add error bars? So here it says with the points, so we can change this to say, and we want errors in both X and Y, so we say XY error here. That's what we want to have. And when we add that command, then it expects us to tell here in this using command, where is the errors. So the format here is that first it comes the X data, then it comes the Y data, and then it comes the error for X data, and then the error for the Y data. And the error for the X data, those are just one column number higher, right? So we need to calculate the error here as well. And how do we do that? So here we have calculated the density. So here we need to do error propagation formula to calculate the error here. So, and because this is just a simple division we're doing here, we're going to add the errors, and the easiest way is to add you adding them, the relative errors you will add together by the square root summation. That's how you do it. So we can start here with the relative error of column 2, that comes in the column 3, that was the column after. So the relative error we need, then we divide by the value of column 2, then we get the relative error, right? So we should take that value in square and add the error of column 4. And we want it to be the relative error, so we divide by the value of column 4, do that in square, and all this we should do the square root of, right? Like that. And then we get the relative error of the density. So if we want to have the absolute value, we need to of course multiply it by the density that we just have calculated. So this will be the error, right, for that whole, for the X dimension. It's easier in the Y dimension because that's only one column, right? So we just take the error which is represented in column 7 because the data was in column 6, right? So we're going to replace that part down here also, so it becomes the same, and with extra errors, yeah, so everything is fine there, I think. So let's say I want it to go from 0.1 on both axes, and then we can also change the format here, so we get 1 decimal in the description here as well. Let's replot and look how it looks like. Now it looks like that, right? So the error in the density is much higher, you see, than it is in this other dimension. All right, so let's change the range here also. So you can see it goes to 256 there. So let's do 256 on both, so it becomes the same aspect ratios or scale on it. Now the data looks like that. So now we see it's the same scale here and same length of scale. So this is important because now we're going to make a model of this, right? A regression line of this. So now it's not a linear data, it's this exponential depending. The data have some exponential dependency. So when we make the scales equal length here, we can sort of, I mean, how do you come up with a model? Well, one way is to plot the data and look a little bit how it looks like. And then we can see if we have a log scale here and log scale here, and then we can look on the slope here. And the slope here seems to be around -2, I would say. It's a negative slope of -2. -1 should be 45 degrees, right? So that indicates that the data set might actually be a dependency that goes to x to the power of -2, right? So 1 over the square of x. So let's make a model around that and fit that to our data, right? So we create a function, and the function, now we cannot make a linear model because it's not, as I said, the model that we are aiming for is something that looks like that. A times x to the power of b, and we believe that b might be -2 here. So if we're going to fit this data now, to fit this model to data, we need to make a linearization of our function as well. So I do that. So I do the logarithm of this. So that will be the logarithm of a plus the logarithm of x times b, right? Oops. Like that, right? And this we're going to fit to the data, right? Fit f log of x to our data. And then it's almost the same syntax, so we just grab everything, and then we can, of course, which data set are we going to fit the data? Let's choose the red data set here now. That was the second data set, right? So we just copy this line, right? Almost everything there. I write here, so it takes that, it uses these parts here, and we don't write with here, but we still want to use the errors here, so we can add the errors here. But remember, when we linearize this, we get the logarithm of the x value here, but we also need to take the logarithm of the y value. So we need to change here. Here it just takes the y value, so we need to add that manually. So it says logarithm of 6 there. And we can do the logarithm of the error perhaps also. Like that. And then we also need to say it should fit via a and b parameters. So let's try that. So here it says that the fitting says the slope is -2.5. So let's plot this function. So we plot our original function here, right? Can make a title, and this is our model, right? Let's give that line style 2 also, because it's the same data set. How does it look like? There we have our line, right? -2.5. So in our model, it's like, okay, this is the dimension of 2.5. That means it has some kind of square root involved there also. Perhaps that can be the case. Perhaps it's more likely that it should be -2 or -3 in this case. So we can, in our fitting, we can force the model to not take the exponent into the fitting here, but we can use that to be a fixed value of -2, for example, and only do the fitting on the A parameter. So let's try that. And it looks like that. So we need perhaps more data points to make a better decision on this. But now we have a -2 slope here, and we only fitted the A parameter. And here we have the standard deviation of that. So this is non-linear data. We have linearized the data set and make a fitting to that data here. So if we want to add the parameters, then we can do that. We can add that to the string here. So let's go back here. We replace this title by the sprintf command, like that, and say that the model we are using here was a times x raised to the power of b, and a was, and then we do the formatting. How big was the number there? 0.26 there. So they can take 3 digits there. So that means it will be 5 and 3 digits. It's a float. If we start with that, yeah, and the b parameter here is we can take the variable, otherwise we could just write -2, but let's take the variable 3.1 f. So, and then we add a and b there as the variables to be important. So if we just do that, you can see here is our model, a times x raised to the power b, where a is 0.268 and b is -2.0. But let's say we want to add the error here now also. You can do that. So the error was, if we look there, that is 0.0405, right? So we could just write the error directly into our value here, and then we can, it depends on how you want to format it, but one classic way is that you add the error within brackets after the number, and that says that the last 2 significant digits has this error. So then, okay, we add that formatting there. Then I need to add the error of of our a parameter. So if I write _error here, I get that number. But then I need to make it 1000 times larger to just get the integer values there. Aha, I missed the decimal mark there. So then it says here, okay, the error is 41 in these 2 last digits, right, of our graph. Okay, now we're going to look on a fifth data set here. We can directly load the data. Let's see, where is my data here now? I load the data, it's this one. So once again, it's electrochemistry, and now it is impedance spectroscopy. So it's the same versus stat unit here, so we recognize the file here, this XML file. And here comes the data. But the new part now is that there are actually 6 different types of measurement within the same file here. So if I scroll down here, you can see that here some other data seems to pop out. And then I can use this every command that we saw in just before in the previous graph, that if I add some blank lines here, then gnuplot can recognize that as block indexes. So then we can pick up one block. So in this data file, there are two impedance spectroscopy measurements, those segments we want to pick out. So I have made blank lines around these data sets in this data file now. Also, you can see that here they are using comma, not semicolon, as the data separator. So we need to fix that also. All right, so we need a graph for this, so we can just start over, I think, with our previous plot 4. We'll make a copy of that. Plot 5, here it is. Say the output is 5. We have a comma here now, a data file separator. The file name of our file, we can remove this fitting now. We're not going to do that. And we can take away everything here. This was the file name, and the impedance data is in column 15 and 16, so we're going to change that here now. So it's column 15 and column 16. But in an impedance spectroscopy graph, one plots the real part of the impedance on the x-axis and the imaginary part on the y-axis. But you also flip it, so the negative direction is upward. So that's the reason why we do the brackets and the dollar sign, so we can invert the sign on the imaginary part. So the X label here we have the impedance real part, and that is in the ohm unit, right? And then we have the same thing here. On the y-axis impedance, but it's the imaginary part in ohm. We need some range there. I think the data is we can do outer range on it perhaps. So just let's set stars for outer range here. And we don't want any logarithmic stuff anymore, so let's remove that and start over. And we don't have any 𝗊𝗆, but we can do, instead of points, we can do lines points. So that means it draw lines between the points. I told you in the beginning that is not the recommended way to do it, because the lines represents the model. But in impedance spectroscopy, you should add a model that actually represents that. But now we don't have any model for this. We're not going to do any model, so we can make the line here. So that is the thing, right? But then we need to choose the data blocks there, and we know if I look in the file, it will be block 14. That is our first data set, and our second data set is in the following block 15. Here it comes. So here is how the data look like. And we only have one data set here. I see that also. So there, I probably missed that part. The other data set is on 16, not 15. It's 16. Oh, we can change line style here like that. Here it is. So there we see the data, right? And in the first data set, we see that there is some weird data points. So there's some error there in the data. So we want to cut out that part. We don't want the first data point to be part of it. So let's work on that first now. So if I write a number here in the beginning, that means if I write a 2 there, I will plot every second row in block 14, right? But that's not what I want. I want to say that I only want to plot from line 10. So I skip the first 10 data points, and then of course I can write something here if I want to end it earlier, but I want to plot everything, so I just do that. So let's do that and replot, and then we look on the data. Now we see that the errors from the black is gone, and we only see the true data there. But then the red one, we see that it's the same problem there, but on the red one it's on the other side also, so it's on the both sides on the red. So if one looks on the data there, we actually need to cut out the first 10 parts and also the last 50 data points, so that to make the graph look proper. So let's do that. Now it looks like this. So there is still some errors on the end there in the second data set, right? But when you have a graph that is like this, so now I have practiced on this every command a little bit more. So it's very versatile, and what shall I say, has a lot of power to it, this every command. So it's very easy to manipulate the data, or picking out the data that you want to plot with the every command. But to continue on this, we can fix the scales here. We see we don't need this point zeros here, right? That's the first part. But also when it comes to impedance spectroscopy, it's very common that one is interested in about the intercept of the left part of the graphs here, where they intercept the x-axis. That means the real part in the high frequency domain. So here it is the low frequency, and here is the high frequency. If you're working with this, you know that's how the line is drawn, but we can explain that in a better way. So we can add a label also to describe that, and then to look on this interesting part here of the intercept. That thing we could make a new graph, so we get a picture in picture, so to say, with a zoomed in version on that, right? So we're going to add all these features now. So let's start adding this formatting and the label there. So we remove the formatting here. It will be only integers, no decimals. That's the first part. And then we can add the label also. So set a label 1 here. We call that, where should it be? Here at, can it say, can we fit it here? 650, 670 and 40. So we uses the coordinates for position. 670 versus 40, right? At, and the label should be, this is the low frequency range, and the low frequency range here is 1 millihertz, I think. And then we can make another label 2 at this high frequency domain. Should we put it down here in the corner perhaps? 350 and 0 and 0. We call that the 1 megahertz, but we cut out mega, so it's actually down now to 100 kilohertz range. That's where the first point is. So let's try that. How does it look like? So now we have a label here saying 1 millihertz, low frequency side, and here's the high frequency side, right? So let's make this zoomed in version now. So if we want to make another graph here, we need to use a command, a different setup here. So we're going to do something called multiplot now. So we add a command in the beginning here before all our else comes into picture. So here it says set multiplot now, And if we're having a title of the graph, then the title will be for this graph that comes beneath here. If you make a multiplot with graphs side by sides and things like that, you perhaps want a title on top of all the graphs. So then you can write title after here, after the multiplot here, to have such a line. But in this case, that's not necessary. So after multiplot, we can make another plot command to replot this data. So I just add that, copycat that down there, and then I write unset multiplot again here to exit that multiplot mode. And because we're going to replot all the data technically, we just want it to be a zoomed in version, so everything will look the same here. The only thing is that we don't need any title, for example, because that is already explained in the previous graph, right? So we can write no title here. That's the first part there. And then we can also how to make it zoomed in, right? That is just the range. So if we look on the range there, we can take a small range in ohm there from 250 to 350 ohm. That's this range, right? We want to zoom in here basically. So then we want something that goes from 250 to 350 and perhaps plus minus 20, we can say there. Minus 20 to plus 20. We want this second graph to be of a different size. So let's change that. Let's the size be, and this is the percentage of the screen size. So it's a 30% width and 30% height. And also we want the position of the graph to start at the, we want it to be in the upper left corner. So it should be like 10% from the left side, and it should be 60% from the bottom, like that. So let's start that also. So there we have our graph, right? And now we see that the labels is also brought along and everything. So we need to unset the labels now before we entering that graph. So here is the label set. So we need to unset label 1 and unset label 2, right? And also we need to unset X label, because we don't need to explain what the scales actually mean, because that we have already defined in the big graph, right? So do unset on all these things, right? And then we can look on the ticks here. It's very tight, so we need a larger spacing there compared to previous. That was the auto ticks, but here we need to change that to something more manual. So let's say 20 in the X direction and 10 in the Y direction. So let's look on that thing now. That looks better, right? And we see also it has this title on top. That can be, of course, useful if we like to have it, but in this case, I think it's everybody knows that that is a zoomed in version of this, so we can just unset the title as well, right? For that zoomed in graph. But there is another thing when we look, and we see that the grid from the background is also in this. So the graph is actually transparent, and that's not so nice, right? It would be much smarter if it has a white background, and to do that one adds an object. One cannot say that the graph should be black. We want to make a white frame in the background there. So then it is say instead of making a label, we're making an object. Now object 1 should be a rectangle, and it should be behind, and it should go from screen position. So this is percentage again, 10% from left and 60% from bottom, to screen 40% from left to 90% from the bottom. So instead of using these percentage numbers, one can also use relative to the scale as we did in the labels, for example. So there are many ways to describe the coordinates, but here using this percentage of screen is very nice. We also want to configure this object one to be of a fill style of solid, a solid line, and we want so we want a black solid line around it, and then we want it to be white on the inside, right, like that. So let's see how that looks like. Now we get that picture in picture there, so it hides a little bit on the data there, so we can adjust that if we change the scale here a little bit. So let's plot it all the way to 0 here on the zoomed out version. All right, so let's go in and change that now. So we want the scale to start, and the data went to -20 in the y direction also, so we can let the zoom in version to handle all that. So let's data go from 0 to 800 and both on the both axes. Normally this data we want it to be symmetrical, not magnified in one dimension. Here it was magnified in the y dimension. So we want the circle should be a circle there, a half circle, not an oval shape. So, and we can also make the command set size square here to make that graph exactly squared shape. I also saw that the data set here should be number 2. There we have 2 data sets. And then since the data is down there in the right corner, so it can be good to move the key to the top right position, so we change that also. And since we are not going in this negative direction, we need to move our picture-in-picture image a little bit inward, so let's add another 5% on that. So it will be something like that. Let's see how this will turn out. All right, so here it looks like that. Yeah, the labels became a little bit cramped there, but we'll let that be for now. So here we have the proper size scales now, so this should be like a half circle according to theory, right? So that's why we want to have the same aspect ratios here. And we have the zoom in version here, so one can go in here and look where it intercepts the horizontal axis. So that is like that dot there could be 295 ohms or something like that. So that's wraps up this part of the bootcamp here. So now we have talked a little bit more about this using the 𝗱command for manipulating the data there when I had different blocks of data and so on, and skipping data within the blocks. And we did this picture-in-picture tool. All right, the next part now is to talk about how to pre-process your data. So that is when you want to do like integration of the data set or derivation or some other kind of manipulation of the data. gnuplot cannot handle that automatically, so you need to use another tool to pre-process the data. And the tool we're going to learn to use today is the 𝗁 programming language. 𝗁 is a simplified programming language that is very neat to use when you're going to manipulate data that is in line data, like exactly as we have here. We have a CSV file. So 𝗁 works similar way as gnuplot. It can add column numbers and look on row numbers and things like that. So what you want to do, you want to download the 𝗁 tool. So you just search for 𝗁, download for Windows. You can download here from this, from SourceForge.net here, for example. Download it. You can find it for other operating systems as well. When you have done that, you can install it system-wide, but I usually just take the exe file and put it directly in the working folder that I have. So let's look on that. Here is my working folder. So here you see I have the awk command now, awk_exe. So then I just click here on the bar and write command here. That opens up the command window in Windows directly in my current working directory here. So here I can run the awk command now, you see here, but now we need to feed it with some commands, and we do the same thing as for gnuplot. We make a script file for this. So let's make a script file. We can create a new file here. We can call that, what shall we call it? Integration of data awk. Let's call it that. So that file in awk, it has 3 different code segments, and it's a very similar syntax to C. So we write like this with curly brackets. So we have the first block, and then we have the middle block, and then we have an end block like that. And in the beginning block, that is things we need to do before we're processing the data. And the middle block here is when we are processing the data, and the end block is after we have processed the data. So for a simple integration, for example, we could add a variable here. We can call it the integral sum, because we need to keep track of the integration. So what actually is integration? Many students are scared about this from the mathematics. It's some hard things, all right? And derivations also is considered to be hard. But let's go back and look on our cyclic voltammeter data. So this can be our data set now. We want to integrate this curve. And in cyclic voltammeter, what does that mean? Well, here we have the dimension of current and dimension of potential, right? Current times potentials, that's power. So the unit is watt. So the area here is some kind of thing that's related to power. All right, so these are all a vast amount of data points, and integration is a sum of function values. That's what integration is. So if we just add the values of each of our our data points, and we add the values together in the columns. We can go and look on the column data here. So we want to sum up. So the current is in the column number 4 here. So these numbers we're going to add up one by one into a large sum, and then we're going to plot that continuously increasing sum versus the voltage that we have in the 3rd column. That will be the integral, but we also need to multiply that sum with the width between the data points. So what is the width between the data points? So the width here is, you have 1 volt all over here, and it's 1000 data points in this file. So that means it will be 1 millivolt between each data point. So we need to multiply the sum by 1 millivolt in the end. But that we can do in the gnuplot as well. So let's go back to the awk scripting now. So here we have the integral sum equals 0. Then we need to tell awk that the data file separator is semicolon. So there's fs we write for that. So file separator is semicolon in this file. And then we also say that the output file that it creates should also have semicolon as separator, because we want that for the gnuplot. And that will be easy to do. Then we come into the middle part here now. We don't need any more in the beginning section. So what are we going to do here? We could add in the beginning section some explanation if we would like to do that. We can write, for example, that the first column is potential and the second column is the integral sum, right? That we could write. And we can make some fancy line beneath the data set here, also before the data starts. And when gnuplot plots the data, gnuplots more or less automatically, if the data is weird, then it just avoids that data. But to be more proper syntax, we can actually make this #square hashtag to make it our official comment for gnuplot also. So then it will just ignore these two lines. All right, so then we go into the mid block here, where we are going to add what are we going to do when we actually processing the data. So if we go back and look on the data file, we see that the data file ends at line 20,120 and it starts at line 131 here, right? So we need to tell AUK to avoid the region outside that. So we only want to process the data within that region. So we use an if statement. And then we have another predefined variable called NR, that is the row number. When the row number becomes larger or equal to 131, then we should start the data processing, and the row number must also be less than 20,120. If those are fulfilled, then we can do our integration, because then we are in the data segment there, right? So what do we want to do? Well, we want to print the current voltage we have on the current row that we're processing, and then we also want to print the integral sum that we have achieved, right? And then we need to actually do the integration. So the integral sum, that is just the integral sum, and then we add the current we have in column 4 to that sum. So that will give us this increasing integration over and over and over again. So that's it, and that's a simple integration. So let's run that script here now. I write AUK f -f to say that we're going to use a script file, and our script is called integration of data, and we make a left arrow to say that okay, now we want to do can I make this larger perhaps? We want to, I can do it like that. What is the data file we're going to work on? Well, this is the data file, right? So if I click enter now, the data just pops up directly on screen here, but that we don't want. We want the data file to go to a file. So then we use the right arrow here, and then we can call this capacity. No, it's not capacity data. What shall we call it? Power data, like that. So then we can find that here. So here we have our data file, and here we also have this little heading that we made before to explain what we're looking on here. So this is the integrated data now that we want to plot. So let's do that. So we make a copy of our old graph, plot 5, right? So make that to plot 6 now. Here it comes. So this will be plot 6. And now you see the data file separator on this old file was semicolon there, so we need to change that. We're not going to use some multiplot stuff here, so we can remove that. We don't need any labels. Square size, we can have square size still, but we can remove all this bottom graph here, so because we only have one plot. Like that. So the data file here is called powerdata.txt, and we're going to plot column 1 versus column 2. And as I said, we needed to multiply this with the width between the data points, which was 1 millivolt, right? And if you look on the data here, you see that it's like a milli range here. So if you multiply it by a factor of 1000 smaller again, it will be in the micro range, right? So if we just multiply it by 1 million here, the final data will be microwatt, right? So the Y label here, that is actually power, and it has the unit microwatt, right? And the X label here is potential and volt, right? But now the cyclic voltammeter is several loops, and we only want to know the integral value for the first part there. So that we only want to look on the first 1000 data points, right? Then we can use the every command for that, right? So now this one was from the previous run where we picked up the block 14, so we don't need that configuration now. But we want to start, you see here, start on line 10. We want to start on line 1, right? And we want to continue to line 1000. So if we write it like that, we should get the first 1000 data points. And then we can use auto range here on the axis here. So let's start with this 0.1 there on the decimal there. Yeah, the data file, it's the separator is semicolon, right? All right, how does the data look like? Here we have the data. So it's many data points. It's the points becomes very close to each other, but we can see that the practical use of this. This is the integral value. You see the integral value becomes negative in the beginning, because if you compare to the graph, it is a negative functional value in the beginning, and then it becomes a positive value, and then here it is almost flat. And when it is flat like that, that means the integral will be a linear sloped line like that. So here we have used the AUK tool to pre-process the data. So now we have the integral value of our measurements. All right, the last part here now of the bootcamp, that is to use AUK in a little bit more advanced way, and that is except just summing up values in the column, or if you want to make a derivation, you would make the difference of each consecutive values. Then you can, because it's a programming language, you can make logical decisions based on what kind of values you have in the columns. And there is a good example where this becomes handy, and then that is in a experiment from electrochemistry again, where we do what we call charge and discharge with a constant current of a cell. So we have a battery cell that we're charging up, and we charge it up with a constant current, and when it reaches the top level of the voltage we want, then we switch and start to discharge it with a constant current again. So what we want to do, that is a way to measure the capacity of the battery or any other cell. It can be a supercapacitor as well. So if we want to measure the capacity, we know the capacity is the current that we are charging or discharging with times the time it takes to fully deplete the cell, right? So that is the current, the capacity. So then we need to tell AUK to look for when the current changes polarity in our potential stat data there. And then take note of the timestamp on that line and calculate the time between these changes. So I already have a script, AUK script for that. I put that up here, and then we can discuss what it contains. So I have the beginning sections. Now it's a different potential stat, so the data file looks a little bit different. So we have a semicolon, a separator here, and the data starts at row 6 and it ends at there's nothing beneath the data, and so we can just say run it to a very large number or until the data set actually ends by itself. Alright, so we put these variables here, so then we can also use data start and things downwards here. File separator, output file separator, we have to keep track of the cycles we are in. We're keeping track on if we are charging or discharging, so we set this value to 1 if we are charging. We call that the positive direction. And then we keep some variables for keeping track of time and the difference between start and stop time. They call that discharge or charge time, depending on where we are. And some current level triggering here. So instead of keeping track when the sign change polarity, because there can be noise sometimes and then it change polarity, it's better to look for when it goes beneath a threshold instead. So we say the threshold is 10 microampere, and in this data file the charging is on 100 microampere, so this is a quite small value. So then we come into the processing data block down here. So the first thing it do, it waits until we come 20 data points into the data, and there it grabs the current value from column 7. So because the current is constant in this constant charge operation, we only need one value basically of that, and that is 100 microampere in this case. We could of course make the script use the current value on each data row, but that can also be a little bit corrupt when we are close to zero potential on the cell there. So yeah, sometimes this is more convenient. And if we are starting the data cell by discharging, we don't want to have that current value that we're going to use for the calculation to be a negative number. So if that's the case, we just change the polarity there. We recognize this from the previous script. We want to process the data when we are within the data section of the data file, right? But here's the new part. There's two if statements now here. And so we're looking on the current value in column 7. If you see, there's two things here. So first, are we in the positive direction? That means, are we charging at the moment the cell? If that's the case, and the current value goes below 10 microampere, that means it switches from 100 plus to minus 100. So we are going into the discharge phase. So if that's happening, then we keep track of the time when that event occurred, and we can calculate how long the charge process has been ongoing. So we take the start time minus stop time, and then we get the charge time there. Then the same thing comes again here, but now we are in the discharge case. So we are discharging, and the current is changing from minus, so it goes above minus 10. That means it has been on minus 100, and it flips up to 100 plus microampere. We do the same thing. We change the mode. Now we are entering the charging phase. Take the time data, calculate the time difference, and now we have also finished a complete charge and discharge cycle. So we add a number on that index there. If you want to add some comment, you can use the hashtag here, so we can just remove that data. We calculate the capacity, as I said, that is the discharge time of the cell divided by 3600, because the time is given in seconds here in the data file. And we multiply by the current, and the current is in milliampere, so then we get unit milliampere hours, right? Last time we just used print and then a bunch of comma values here, but we can also format the output. So printf, same as sprintf in gnuplot. You see here we have the formatting string, and then we add the variables that we want to plot out. Here's some old stuff also that's been commented out. We don't need that either. So that's our script, right? So let's try to run that now in our command box here. So where are we? Here is our command box. So we go in here, start the awk, use the script called grab data. We want the data called data, no, not that, data log, it should be called data log there. Send it to a file called capacity data text. Let's look on the data now, how the file came about. So here, how it looks like. So now you see we have a nicer formatting here, so they are in good tabular order as well, so for visual inspection. But we are only interested in the capacity here and the cycle number. So the capacity we see is in the power of -3 of milliampere hours. So that means it's like microampere hours actually we are having capacity here. So we can change that now in gnuplot. So let's plot this now in gnuplot, so we can copy our old plot. What was that? Plot 6, and make a plot 7. Like so. So okay, here is plot 7. We only have cycle numbers that they are integers on the x-axis, so don't need any decimals there. We'll see if we need decimals on the y-axis. I don't think so. Let's use out on both of these. So this is capacity of cell being cycled. X label is cycle number. Capacity, and it will be in microampere hours, right? We don't need any square shape here. I don't think that is actually, we usually want it to be like longer in this case compared to its height, so I make it twice as long as its height. Capacity data there, and we can also plot the full range, out the range there, and we plot column 1 versus column 2, but we want to make that 1000 times larger to get milliampere hour to become microampere hours. And we don't need to jump over any data, we plot just everything. And normally when we make a plot like this, we don't want to make a line between, usually a box plot or something is more proper here. So we can choose that also because we haven't demonstrated that yet. So let's say boxes here. And we can use some formatting of it. So we want to make it a solid box or a little bit transparent box like that. And let's check how the data look like. So here is the data set now, right? Here we have cycle number, and here we have capacity. So, all right, so we actually would need to have a formatting on the capacity there that gives like 1 decimal. So let's add 1 decimal there on the formatting. So we have capacity in microampere hours there, so it's like 1 microampere hour, and we see it's declining after each cycle here. Capacity of cells being cycled, and we have cycle numbers here. So this is the final example of how to use gnuplot in our bootcamp, where we have used the awk tool for a second time to pre-process our data into this new data set here. that ends the bootcamp. So now we have gone through a very vast list of operations. So the point with this bootcamp is to make you leave the Excel space and enter into some more professional way of making graphs. And with gnuplot, the learning thresholds is quite small. With the stuff that you have seen now, you can solve like in 95% of all your plotting work that you need as a researcher. And yeah, the more advanced stuff that you're going to need, that thing you can figure out from yourself now on. So you can just build on these things. And remember that you can go to this demo page at the gnuplot.info to see all these code snippets, how to make different things. That is the first place to start. You can also go to like Stack Exchange where all users write all kind of magic ways of make very fancy graphs and so on. But that is the thing. And I mean, just to summarize, we learned how to install the gnuplot, how to set up and make a proper graph, that we're going to use files. We talked about how a proper scientific graph should look like. We fixed so we can make like Greek symbols in this labels there, and it also made this learned how to choose the different data blocks of the data being processed. We made error bars, we made linear regression, and we put the variables that and the linear regression calculated for us. We put that directly into our graph so we can see the numbers in our model that we're using. We looked on data that is not linear, so we needed to make a linearization of that data first. There's a lot of things we have been doing here, and we also looked on how to change this length of the fitting line and so on, and only fit it to a certain part of the data. And then also talked about how to make like a picture in picture, so a zoomed in graph of the graph, and so on. And finally we came to this 𝗁𝗀 tool, how to pre-process our data to make like simple integrations or some other simpler stuff to pre-process our data. So that's it. I hope it helped you out.